Hello guys, welcome to another video. Today we're going to work on topic 10, fields for HL. We're going to see a couple of problems from past papers, so let's jump straight to the paper and see the solutions. The first question says, two plastic rods each have a positive charge plus Q situated at one end. The rods are arranged as shown. Assume that the change at the end of each rod behaves as a point charge. Draw in the shaded area on the diagram, first, the electric field pattern due to the two charges. So now you see that you have two positive charges, let's say that they're just point charges, it says here. So what do? We create the electric field of those. Of course, you know that the electric field is gonna be in this direction, and of course, each lines, they will be pushed away from the other charge. So you have something like so. You don't have to make many lines, and of course you need to show the direction of the lines, so it's always repulsive, so away from the point charges. And the number 2, it says, draw a line to represent an equipotential surface. Label the line with the letter V. Of course, we need to label that in order to separate it from what we see here. Now, equipotential, you have to remember that it's always perpendicular to the field lines. So I'm gonna draw here one equipotential line. You can draw it wherever you want. Just be sure that it looks like vertical with every other field line. And you label this with a letter V. The part 2 is about orbital motion. It says that a satellite of mass m is in orbit about Earth at a distance r from the center of the Earth. Deduce that the kinetic energy of the satellite is equal to half the magnitude of the potential energy of the satellite. So now, in order to calculate kinetic energy here, first we need to define speed. And what do we know here? We know that the Newton's law of gravitation now, it is equal with the centripetal force on the satellite. So that means that gmm over r square is equal with a mv square over r. The small m, of course, is the mass of the satellite. So these they cancel out, the r with the r squared cancels out. So from here you solve for v or for v square, because the kinetic energy have v square, so we don't have to solve for v, and then rearrange it again. So now what do? We need to calculate kinetic energy, that it is 1 over 2 mv squared. So this is 1 over 2 g mm over r, based on what you saw before. Now the potential energy, what is it? It's minus g mm over r. So you see? So it's half. And of course this formula you get it from the data booklet. And these are your 3 points that you need to make in order to solve this exercise. The next one, it says that the graph shows the variation with distance r of the Earth's gravitational potential V. Values of V for r smaller than the capital R, where the capital R is the radius of Earth, are not shown. So we don't care about what's happening from here and below. The satellite in A has a mass of 8.2 times 10 to the power of 2 kilograms. And it is in an orbit at a distance of 1 times 10 to the power 7 meters from the center of the Earth. Using data from the graph and your answer to A, calculate for the satellite its total energy. So total energy, first of all, for the satellite, it is what? Is the kinetic energy plus the potential energy that it has. We just calculated before. So it is 1 over 2 gmm over r minus gmm over r. So from here, you have minus 1 over 2 gm over r. But this gm over r, it is the potential. So the total energy, it will be equal with minus 1 over 2, the potential, the gravitational potential, times the mass of the satellite. So from here, you know that at this specific distance of 1 times 10 to the power of 7, what do you have here? Your potential, it has this value. So this is equal with 1 over 2 times 4 times 10 to the power of 7 times the mass of the satellite, 8.2 times 10 to the power of 2 So this will give you a value of 1.6 times 10 to the power of 10 joules, of course, with negative value if you want to carry it. Number 2, it says its orbital speed. Now the v-orbit, it can easily be found in your data booklet. It is actually the one that you calculated in the beginning. So it is given by this formula. So actually it's the square root of Vg, of course at the same point. Of course here we take the absolute values for Vg. So if you do the math here, you are going to find with the correct substitutions, you have the square root of 4 times 10 to the power of 7. Of course you cannot solve this one, so you need to do the square root of 40 times 10 to the power of 6 to take everything out of the square root. So the v-orbit, it will be equal with 6.3 times 10 to the power of 3 meters per second, of course, units, everything is in SI, so you don't worry about it. And number 3, it says, the energy it must gain to move to an orbit at distance 2 times 10 to the power of 7 meters from the center of the Earth. So, what do we do here? First, we need to calculate how much total energy it will have in the new orbit. So, let's call it total energy prime, and it will be based on the formula before that you have here, minus 1 over 2, the Vg prime, the new one. So, at 2 times 10 to the power of 7, you can see that it has this value. So you substitute here, it's minus 1 over 2 times 2 times 10 to the power of 7 times 8.2 times 10 to the power of 2. So if you do the math here, the new energy that you want, it will have a value of minus 0.82 times 10 to the power of 10 joules. So the energy required, the required energy now, of course it will be the subtraction between those two values. So it will be the total energy minus the new total energy. Of course here you can ignore the negative sign, so it's 1.6 times 10 to the power of 10 minus 0.82 times 10 to the power of 10. So the required energy, it will be 7.8 times 10 to the power of 9 joules, if you round it in the two significant figures that we want. Now the next one, it says define electric potential at a point in an electric field. Again, here is a definition that we cannot lose marks from that. So 3 marks, so we have to make 2 points. And first, you say the work done per unit charge when a test positive charge is moved from infinity to a point. And these are your 3 points that you need to make in order to state this definition correct. Now 46b, you have a positive point charge that is moving towards a small charged metal sphere along a radial path. At the position shown in the diagram, the point charge has this speed, 3.5 meters per second, and is at a distance 2.78 meters from the center of the metal sphere. The charge of the sphere is 4 microcoulombs. The first one, state the direction of the velocity of the point charge with respect to an equipotential surface due to the metal sphere. So for the first one, we just need to state the direction of the velocity. So in order to do that, we need to figure it out the equipotential line here. Of course, the metal sphere, it will create an electric field in these directions, like so. And the equipotential, it's gonna look as we did before. It needs to be perpendicular to every single one of those. So it's gonna look something like that. Okay, perpendicular to every one of these. And now you see that the velocity, it is in this direction here. So at this point, it's gonna be perpendicular as well. So your answer here for A, it is perpendicular. The number 2, show that the electric potential V due to the charged sphere at a distance of 2.78 meters from its center, it's 1.29 times 10 to the power of 4 volt. So this is again something very simple. We just apply the formula for potential, that is K times Q over R. So this it is, the constant K, it's 8.99 times 10 to the power of 9. The charge, it's 4 times 10 to the power of negative 6 coulombs. The distance, it's 2.78, predetermined from here. you do the math, you find a value of 1.29 times 10 to the power of 4 volts. Nothing hard here, just be careful to use the correct constants from your data booklet always. And the number 3, it says the electric potential at the surface of the sphere is 7.2 times 10 to the power of 4 volts. The point charge has a charge of 0.0320 microcoulombs and its mass is 1.2 times 10 to the power of negative 4 kilograms. Determine if the point charge will collide with a metal sphere. You see that you have the mass and the velocity of the point charge, so you can know how much it is its kinetic energy. So you need to see if this kinetic energy will be enough in order to bring it at this point here. And in order to see how much energy is needed for that, you need to see first the difference in potential. So the difference in potential, it will be the potential at the surface of the metal sphere, let's call it V prime, minus the potential that currently the charge is. So it's here, we just calculated before. So from here, that's why it said solve this value. So if you cannot solve this part, you can at least move to the next one. So here what do you have? You have 7.20 times 10 to the power of 4 minus 1.29 times 10 to the power of 4, and this will give you a value of 5.91 times 10 to the power of 4 volt. Now that you have the potential, you need to see how much energy it will lose from all the way from here to here. And of course, this loss in energy, let's call it delta E, the value of charge of Q times the difference in potential. So from here, what do you have? 0.0320 times 10 to the power of negative 6 coulombs times 5.91 times 10 to the power of 4 volts. So now you find this loss in energy that it will be equal with 1.89 times 10 to the power of negative 3 joules, if you do the math. And now what is left is for you to calculate the energy that the charge has, and of course this is the kinetic energy, it's 1 over 2 mv square. You have everything here, this is square, so you have 1 over 2 times 1.2 times 10 to the power of negative 4 times 3.5 square. And if you do the calculations, you are going to find a value of 7.3535 times 10 to the power of negative 4 joules. So you see here that this energy, it's not enough to cover this energy that you're going to lose in order to move from one point to another. So not enough energy, so it will never collide to the surface of the sphere. And this is how we solve this problem. This part, I can admit it's a little bit difficult, not difficult, but you just have to do like 3 points, 3 steps in order to solve. Now the next one, it says explain what is meant by escape speed. So escape speed, it is the minimum speed of an object at the surface of the planet in order for this object to escape the gravitational field of the planet. And this is escape speed. Now the next one, it says that Titania is a moon that orbits the planet Uranus. The mass of Titania is 3.5 times 10 to the power of 21 kilograms. The radius is 800 kilometers. Use the data to calculate the gravitational potential at the surface of Titania. So here for number 1, we have nothing more to do than just application of the formula that you can find in your data booklet, and you have everything. You have the mass, you have the radius, and so on. So if you do the math here, I'm not going to spend time solving that. It's 2.9 times 10 to the power of 5 joules per kilogram. And number 2, use your answer to B1 to determine the escape speed of Titania. So the number 2, the escape, again, you can find this definition from your data booklet. It is the square root of 2gm over r, or otherwise you can just say that the kinetic energy and the gravitational potential energy, they must be 0. So if you do the calculations here, you're going to reach this formula, of course. So the V escape actually is what? Is the square root of 2 times Vg. Okay, as you can see from the combination of these formulas. Anyway, it doesn't really matter, you have everything here. You don't need to worry about that. If you do the math, you are going to find this value, 7.6 times 10 to the power of 2 meters per second. Now, the 47C, it says that an astronaut visiting Titania throws an object away from him with an initial horizontal velocity of 1.8 meters per second. The object is 1.5 meters above the moon's surface when it's thrown. The gravitational field strength at the surface of Titania is 0.37 newtons per kilogram. Calculate the distance from the astronaut at which the object first strikes the surface. Okay, so here it's something from topic 2. What do you have? You have here the surface of Titania. The astronaut throws an object from 1.5 meters height. So the object, it moves in this direction with a horizontal velocity of 1.8 meters per second. So it's gonna make this projectile motion, and you try to calculate this specific distance s. In order to do that, of course, we need to find the time that it needs to move all the way down, but we need to work first in the y-axis in order to do that, and then we work in the x-axis in order to calculate distance. So for the y-axis, you're going to use one of the kinematic equations to calculate time. So from here, it's pretty easy to do that. Be careful here, don't use g of 9.8. You have this g, is 0.37. So the time for the flight, it is 2.85 seconds. You have everything in order to calculate it. And of course, the velocity in the x-axis, it will be equal with the distance in the horizontal axis divided by the time. So the distance will be the velocity times the time. You have everything 1.8 times 2.85. It will give you a value of 5.1 meters. And the last one, 48A, state in words Newton's universal law of gravitation. So it specifies here in words, so you cannot just say F is equal to gmm over r square. This is not acceptable. So what we need is to just explain this formula with words. So we say that the attractive force between 2 point masses, and be careful here, the word point is very important. What it is proportional to the product of the masses. Be careful here, don't say just proportional to the masses, it's the product of the masses. And of course, inversely proportional to the distance square between them. And this is how we state Newton's universal law of gravitation. So that was all for today, guys. Be sure that you understand everything in this topic and study hard, and good luck.